The shift bell rang at 6. Along the riverfront, factory windows dimmed one by one as men pulled on coats and left their stations. Another day ending like all the others. The steam plant wound down through its familiar sequence. Dampers closed, feed water stopped, blowdown valves secured. The fireman made his final rounds, banking what little remained in the fireboxes, feeling the heat beginning its long retreat into the evening air. By 7, the boiler house stood quiet. The main unit, a massive horizontal return flue design, sat cooling in the dim light. 10 feet long, 5 feet in diameter, its iron shell still radiated warmth, but that was expected. Metal that size took hours to release the day's accumulated heat. The needle on the main pressure gauge had fallen from 120 pounds to perhaps 40. Normal. Predictable. The system was doing what it always did. The night watchman walked through at 8. He noted nothing unusual in his log. The space was warm as it should be. The iron ticked and settled as it always did. Outside, the river moved past in darkness, and the city's lamps began to glow against the autumn sky. But somewhere in that dimness, something had not finished. The boiler house was not cooling the way it should. Not yet obviously wrong, but subtly, persistently different. The air inside the brick walls held its heat with unusual tenacity. The metal surfaces, when touched, felt warmer than they ought to be this many hours after shutdown. The pressure gauge, which should have continued its steady decline, seemed to have stopped falling. 40 pounds. Still 40 pounds. The needle trembled slightly, as if uncertain. No one was there to notice. The building sat alone in its residual warmth, the massive iron cylinder at its center, still holding the day inside itself, refusing the night's invitation to grow cold. The fire was out. The steam lines were closed. Everything had been done correctly. Yet the heat remained, pooled in metal and water and brick, moving in ways the men who built the system had not quite accounted for. The stack rose 30 feet above the roof, a brick column open to the sky. No smoke emerged. No heat shimmer disturbed the stars, but air moved inside it nonetheless, sliding down the interior walls in slow currents, finding its way into spaces that were meant to be sealed. The chimney was drawing, even without fire, pulling cool air down into the system, pushing it through gaps and clearances the designers had considered irrelevant. A breath so slow it made no sound. Inside the boiler shell, hundreds of gallons of water sat trapped between iron plates. The mass was enormous, its thermal inertia profound. It cooled, but not quickly. As the surface temperature dropped, condensation formed on every cool surface nearby. Droplets gathered and fell. Each one released a small measure of heat back into the air. The moisture migrated, seeking equilibrium, creating tiny pressure differentials in sealed spaces. The factory slept, the river moved, and the boiler house remained warm. Dawn found the day foreman arriving early, as he often did, walking the floor before the men came in. He stopped at the boiler house threshold and felt what the night watchman had felt. Warmth, persistent, unexplained warmth. He stepped inside and placed his palm against the iron shell. Heat radiated through his glove. His eyes went to the pressure gauge. 42 pounds. Not 40, 42. He stood there, frowning, trying to make sense of it. The boiler had been shut down for 12 hours. The pressure should have dropped to nothing by now, or nearly nothing. Instead, it had risen. Not much, but enough to be wrong. He checked the logbook, read the watchman's note from 3 in the morning, then walked the perimeter of the unit, looking for something out of place. By 7, the morning crew began to filter in. The fireman arrived and immediately noticed the warmth. He went straight to the dampers, checked them twice, then looked at the foreman with confusion. Everything was closed. Everything was as it should be. But the heat was still there, and the iron was still radiating like it had work left to do. Word spread quietly through the floor. Men gathered near the boiler house entrance, not quite entering, talking in low voices. Someone suggested a valve had been left open. Someone else said the gauge was faulty. A third man, older, with years on steam systems, said nothing at all. He just stared at the iron shell with an expression that might have been recognition or might have been fear. The foreman ordered a complete inspection. Every valve, every fitting, every connection point. The crew moved through the system methodically, calling out positions as they went. Main steam valve closed and seated, feed water closed, blowdown closed, auxiliary lines closed, safety valve free and clear. Nothing was open. Nothing was leaking. The system was isolated exactly as it should be. But the warmth remained, and now in the morning light they could all feel it, not the fading warmth of residual heat, but something that felt almost sustained. The air in the boiler house was heavy, thick, unmoving. The iron hummed faintly when touched, a vibration so subtle it could barely be felt. One of the younger workers pressed his ear against the shell and pulled back quickly, unsettled. He said he heard something inside. Movement. Water, maybe. Or pressure equalizing. Or something else. The foreman told him to step back, told all of them to step back. He wrote in the logbook, "System remains warm 12 hours post-shutdown. All valves confirmed closed. Pressure holding at 42 psi. Cause unknown." He underlined the last two words. The factory whistle blew for the morning shift. Work resumed everywhere else. But the boiler house stood apart, warmer than it should be, holding on to something the men could not yet name. The decision was made to watch it through another night. The building was sealed properly this time, every door checked, every access point confirmed. The main boiler sat in the center of the space like a sleeping animal, its iron skin still radiating warmth into the brick walls. The foreman assigned 2 men to stay through the dark hours, checking the gauges every hour, logging any changes. They were not to touch anything, not to open anything, only to watch. The men settled in as the light faded. They brought lanterns and coffee and a small stove for warmth, though the boiler house itself needed no additional heat. The iron ticked occasionally, deep structural sounds that seemed to come from inside the metal itself. The pressure gauge held steady at 42 pounds, its needle fixed in place, as if pinned there by some invisible force. At 9, one of the men walked the perimeter again, running his hand along the shell. The warmth was uniform, no hot spots, no cold areas, just consistent, persistent heat that had no reason to be there. He returned to his chair and made a note in the log. Nothing to report, nothing changing, but the wrongness of it sat in his chest like a weight. At midnight they heard it clearly for the first time. A low hum, barely audible, coming from somewhere inside the boiler. Not constant, but rising and falling in slow waves. They both stood and moved closer, listening. The sound was there, then gone, then back again, like the system was breathing. One man suggested it was water shifting. The other said water did not make that sound. Then came the knocking, dull, distant, muffled by iron and water. 3 slow strikes, evenly spaced, then silence. They waited. Nothing. Then minutes later, 3 more, same rhythm, same spacing. One of the men touched the shell and felt the vibration travel through the metal. Something inside was moving, striking, settling. The laws of pressure and temperature working themselves out in ways that felt deliberate but could not be. At 2 in the morning they heard a different sound, a long, low sigh like air escaping under pressure. They checked every valve, every fitting. Nothing was open, nothing was leaking. But the sound continued, faint and regular, coming from somewhere in the system they could not identify. The pressure gauge still read 42 pounds, had not moved in 18 hours. One of the men wrote in the log, "Sounds from inside the unit, cause unknown, pressure unchanged." They did not speak much after that, just sat and listened to the boiler house tick and hum and occasionally knock. The iron was not cooling, the pressure was not falling, and the sounds, whatever they were, continued through the darkness like a language neither man could understand. When the foreman arrived at dawn, he found them both awake, tired, unsettled. They handed him the logbook. He read it twice, then looked at the gauge. 42 pounds. Still. He placed his hand on the iron shell and felt the warmth that should not be there. The building was wrong. The system was wrong, and no one yet knew why. The engineer was summoned from the city. He arrived on the noon train, carrying a leather case and an air of professional certainty that the factory men found both reassuring and faintly irritating. He walked the system with the foreman, asking questions, checking drawings, examining every component with the methodical attention of someone who had seen boiler problems before and expected to see them solved. He started with the pressure gauge, removed it from its fitting, inspected the internals, blew through the line to confirm it was clear. The gauge was accurate. 42 pounds was real. He reinstalled it and moved on to the valves. Each one was opened and closed, the seats examined for scoring or debris. Everything was clean. Everything was tight. The isolation was complete. He checked the water level through the gauge glass, still nearly full. Hundreds of gallons sitting inside the shell, held between iron plates 3/4 of an inch thick. He calculated the thermal mass in his head, estimating cooling rates, comparing them to what the gauge was showing. The numbers did not align. The boiler should be cold by now. The pressure should be gone, but it was not. The engineer spent an hour examining the stack. Climbed to the roof, looked down the interior, checked the dampers at the base. Everything was closed. No draft should be possible. Yet when he held his hand near the base of the chimney, he felt air moving. Barely. A faint current, cool and descending. He frowned and made notes in a small book he carried. Something was moving air through the system, something subtle, something the builders had not anticipated. By late afternoon, he had completed his inspection. He gathered the foreman and the senior crew in the boiler house and delivered his assessment. The system was mechanically sound. No leaks, no failures, no operator error. But the thermal behavior was anomalous. The mass of water inside the shell was resisting normal cooling. The chimney was creating a reverse draft, pulling cool air into spaces it should not reach. Condensation was forming and releasing heat back into the system. Pressure was equalizing across temperature gradients in ways that appeared to generate steam without fire. One of the older workers interrupted. He asked if the boiler was dangerous, if it could fail. The engineer paused, choosing his words carefully. The pressure was low, far below the design limit. The safety valve would lift long before any risk emerged. But the behavior was wrong. Not dangerous, but wrong. And wrong systems had a way of becoming dangerous if left uncorrected. He recommended bleeding the pressure manually, opening the blowdown valve slowly, releasing whatever force was trapped inside, allowing the system to equalize with the atmosphere. The foreman agreed. The crew stepped back. The engineer positioned himself at the valve, hand on the wheel, and began to turn it open. Nothing happened. The valve opened. The line was clear, but no steam emerged, no pressure released. The gauge needle did not move. 42 pounds, still 42 pounds. The engineer closed the valve, confused, opened it again wider this time. Still nothing. The pressure was there, registered on the gauge, but it would not bleed off. He stepped back, staring at the gauge. The crew stood in silence. Someone had made a mistake. Something had been misunderstood, but no one yet knew what. The boiler was isolated. The pressure was real, and it would not release. The system was working against itself in ways none of them had encountered before, following laws they could not quite see. The engineer returned the next morning with additional instruments. A differential pressure gauge, a thermometer set, a notebook filled with calculations from the previous night. He moved through the boiler house like a man solving a puzzle, measuring temperatures at different points on the shell, checking pressure across various sections, mapping the thermal gradients in careful detail. What he found was subtle. The boiler was not uniformly warm. The top surface was cooler than the bottom by nearly 20 degrees. The ends were cooler than the center. The flue passages inside showed different temperatures depending on their position relative to the water. The system was not cooling evenly. It was cooling in layers, in zones, creating internal currents and pressure differentials that the gauges could not fully capture. He examined the pipe connections more carefully this time, noted the angles, noticed how condensate would naturally flow back toward the boiler shell in several lines that sloped incorrectly, saw how water could accumulate in pockets, releasing heat slowly, creating localized steam pressure that could not escape because the valves above it were closed. Each small imperfection in the installation, irrelevant during normal operation, became significant during shutdown. The fireman pointed out something the engineer had missed. The brick setting around the boiler was not just structural. It was thermal mass. Thousands of pounds of masonry that had absorbed heat for years, radiating it back into the air even when the fire was out. The building itself was a heat reservoir, keeping the boiler warmer than ambient temperature, slowing its cooling beyond what calculations based on the unit alone would predict. Another detail emerged. The feedwater line, though closed at the valve, was full of water all the way back to the supply tank. The column of water, exposed to the warm air of the boiler house, was warmer than the supply tank itself. Thermal convection was creating a slow circulation through the closed system, moving heat from the boiler house back into the tank, then back into the feedwater line, then back toward the boiler. A closed loop that sustained itself without pumps or valves being open. The engineer made sketches, drew diagrams of the system as it actually existed, not as the drawings showed it. He marked every slope, every pocket, every place where water could accumulate or air could move. The factory men watched him work, beginning to understand that the problem was not one thing but many things, all interacting in ways too subtle to see without looking carefully. By afternoon, he had identified another factor, the safety valve itself. During operation, it lifted occasionally to release excess pressure. Each time it did, a small amount of scale and sediment was blown through the seat. Over years, microscopic damage accumulated. The valve still functioned, still sealed, but not perfectly, not absolutely. When pressure differentials across the valve reached certain thresholds, tiny amounts of air could pass in either direction, equalizing pressure in ways that appeared impossible if the valve was assumed to be completely tight. And there was the matter of the water mass itself. 300 gallons, 2,500 pounds, sitting inside an iron shell in a warm room, cooling at a rate of perhaps 1 degree per hour. At that rate, it would take days to reach ambient temperature. Days during which condensation would form, air would move through imperfect seals, pressure would equalize across temperature zones, and the system would behave in ways that seemed wrong, but were only following laws the builders had not fully accounted for. The engineer closed his notebook. He had no single answer, only a collection of small truths that together explained what the gauges showed. The boiler was not broken. It was simply doing what it was built to do under conditions no one had properly considered. The wrongness was not in the machine. It was in the expectations. The foreman asked the question all of them had been thinking. If there was no fire, how was the chimney drawing air? The engineer led them outside to the base of the stack. He explained what he had observed, what the measurements confirmed. The chimney was operating in reverse. During normal operation, hot gases rise through the stack, creating draft by the difference in density between hot and cold air. The column of hot air inside is lighter than the column of cold air outside, and the pressure differential pulls combustion air through the firebox. Simple, predictable. But when the fire goes out, the column inside cools. And if it cools faster than the masonry around it, something unexpected happens. The brick of the chimney holds heat, days' worth of heat absorbed from years of operation. Even with no fire burning, the masonry radiates warmth inward. The air column inside the stack is warmer than the outside air, but cooler than the brick. Convection currents form. Warm air from the brick heats the air at the walls of the stack. That air rises, but the center of the column, exposed to the cooling night air above, sinks. The stack becomes a circulation system, moving air downward through its center, upward along its walls, creating a draft without fire. The engineer traced the path of the air, down through the stack, into the smoke box, through the flue passages of the boiler where residual heat warms it slightly, then out through gaps and clearances in the brick setting. The air does not exit through the stack because the damper is closed. Instead, it finds other paths, leaks around doors, gaps in the masonry, small openings that matter not at all during normal operation, but become significant when pressure differentials reverse. One of the crew asked if this could sustain heat in the boiler. The engineer shook his head. Not sustain it, but slow its loss. The moving air carries heat from the brick setting to the boiler shell, distributing thermal energy that would otherwise radiate away more quickly. It creates a convective loop that keeps the entire system warmer than it would be in still air. Not much warmer, a few degrees, but enough to change the cooling rate, enough to confuse men who expected simple, predictable decay. They returned inside. The engineer placed his hand near the base of the stack, feeling the faint downward current. He moved to the smoke box door and detected air movement there as well. The system was breathing, slowly. imperceptibly unless you knew to look for it, but continuously redistributing heat, equalizing pressure, following the path of least resistance through a machine that was not, after all, sealed as tightly as everyone had assumed. He explained further. Every valve, every door, every joint in the system was designed to withstand internal pressure pushing outward. The seals were adequate for that purpose, but they were not designed to prevent air from being pulled inward by vacuum or drawn through by subtle pressure differences. The reverse draft created conditions the builders had not anticipated. The boiler was not designed to shut down. Not really. It was designed to operate. And when operations stopped, the gaps in that design became visible. The factory men absorbed this slowly. The idea that the chimney could draw without fire, that air could move through a system assumed to be closed, that the building itself could participate in sustaining warmth, all of it ran counter to their practical experience. But the engineers' measurements supported it. The faint movement of air was real. The thermal patterns were real. The system was doing exactly what physics required, even if common sense suggested otherwise. One man asked if they could seal it completely, block the stack, close every gap, eliminate the circulation. The engineer considered this, possibly, but doing so might create worse problems: vacuum formation, differential pressures that could collapse flues or damage the shell. The machine had evolved to handle these forces through small leaks and pressure relief. Sealing it completely might just trap the problem rather than solve it. The boiler needed to breathe, even in shutdown. The builders had known this, though perhaps not consciously. They had left gaps, clearances, relief paths, and those paths were now doing their work. The engineer spent the next day focused on pressure behavior. He attached the differential gauge across various sections of the system, measuring pressure differences that the main gauge could not show. What he found confirmed his suspicions. The pressure inside the boiler was not uniform. It varied by position, by temperature, by the presence or absence of water. The shell itself contained 3 distinct zones. The lower section, full of water, showed higher pressure because the water mass resisted cooling and generated vapor pressure as it slowly equilibrated with the warmer brick setting. The upper section, filled with steam space, showed lower pressure because the air there cooled faster and contracted more readily. The flue passages, filled with trapped air and residual moisture, showed intermediate pressures that shifted as condensation formed and evaporated. When the blowdown valve was opened, it accessed only the lower water section. That section was essentially incompressible. Water does not expand into a pressure release the way steam does. The valve opened to liquid, and liquid simply sat there, held in place by its own mass and the pressure of the water above it. No release occurred because there was nothing to release. The gauge showed pressure from vapor in the upper section, but the valve could not access that vapor because water blocked the path. The engineer demonstrated this by opening a vent at the top of the shell, a small valve used during filling to release air. When he cracked it open, steam hissed out immediately. Not much, not sustained, but enough to prove the point. The pressure was there in the vapor space, but trapped above a mass of water that could not be easily removed through the normal drain paths. He explained thermal contraction next. As the iron shell cooled, it shrank. Microscopic amounts, but measurable. The shell's volume decreased, creating a slight vacuum that pulled air inward through any available gap. The reverse draft through the chimney was fed by this vacuum, which drew cool air down into the system to replace the volume lost to contraction. The incoming air was then warmed by the brick setting and the residual heat in the metal, expanding again, creating pressure that registered on the gauge. Condensation played its role as well. Every surface inside the boiler that was cooler than the steam temperature became a condensation site. Water vapor condensed into liquid, releasing its latent heat into the surrounding metal and air. That heat slowed cooling in nearby zones, creating temperature differentials that drove further condensation elsewhere. The process was self-sustaining at a low level, a slow exchange of phase change energy that appeared to generate heat from nothing, but was merely moving heat from one form to another. The pressure gauge, reading from the steam space, showed the combined effect of all these processes. vapor pressure from the warm water below, expansion pressure from air drawn in and warmed by the brickwork, contraction vacuum from the cooling iron, equalization pressure from condensation releasing heat. All of it summed to 42 pounds, a value that appeared stable but was actually the result of dozens of small forces in constant flux, balancing against each other. One of the crew asked why the pressure had increased slightly from its low point at shutdown. The engineer pulled out his calculations. At shutdown, when the fire was first damped, the boiler held residual pressure from operation. As it cooled, that pressure fell rapidly. But as the system approached ambient temperature, the cooling slowed. The brick setting continued radiating heat. The reverse draft began moving air through the system. The water mass, enormous and slow to cool, began to dominate the thermal behavior. At some point, the heat being added back by these processes balanced the heat being lost to the environment. The pressure stopped falling. In some hours, particularly warm ones, it even rose slightly as localized heating exceeded localized cooling. The pressure was turning against itself. The system, built to generate and release steam under operator control, was now generating and trapping pressure through passive processes no one controlled. It was not dangerous. The forces were too small, but it was persistent, and it would continue until the water mass finally cooled to ambient or until someone intervened to break the cycle. The engineer presented his final conclusions to the factory management. He stood in the boiler house with his notes and diagrams, the warm iron shell behind him. The crew gathered to hear what months of mystery had reduced to. There was no hidden fire, no fuel source, no chemical reaction, no external heating. The boiler was cooling, but it was cooling slowly through a system that was not designed with shutdown dynamics in mind. Every element of the design, the massive water reserve, the brick setting, the chimney draft, the valve arrangement, served the purpose of sustained operation. In shutdown, those same elements worked against rapid cooling. The reverse draft was real, measurable, caused by temperature differentials between the masonry and the air column in the stack. The draft moved air through the system, redistributing heat from the brickwork to the boiler shell, slowing the overall cooling rate. The effect was small, a few degrees difference over many hours, but cumulative. The builders had understood draft during firing. They had not considered what draft would do without fire. The water mass was the primary factor. 2,500 pounds of water sitting inside an iron shell, cooling at perhaps a degree per hour. The thermal inertia was enormous, and as it cooled, it released vapor into the steam space above, maintaining pressure through simple evaporation, not boiling, not steam generation in the conventional sense, just slow evaporation from a warm water surface in an enclosed space. Enough to show on the gauge, enough to persist for days. Condensation feedback explained the rest. As vapor condensed on cool surfaces, it released heat. That heat warmed nearby water, which evaporated slightly, releasing more vapor. The cycle was inefficient, losing more heat than it gained, but it slowed the approach to equilibrium. The boiler was not heating itself. It was simply releasing the heat it contained in ways that appeared to generate pressure. The pressure measurement itself was misleading. The gauge read from the steam space, showing vapor pressure from the water below. But that pressure was trapped above a liquid mass that prevented it from being released through the normal blowdown path. Opening the bottom valve drained liquid, not steam. The pressure remained because the pressure source, warm water, remained. Only by venting from the top could the steam space be truly released. The valve seats, examined under magnification, showed wear. Microscopic gaps that allowed air movement under certain conditions. Not enough to leak during operation, when internal pressure exceeded external pressure by large margins, but enough to allow equalization when the pressure difference was small and reversed. The valves were working as designed. The design simply had not accounted for this mode of operation. Thermal contraction of the iron shell created vacuum effects. As the metal cooled and shrank, volume decreased. Air was drawn inward through every imperfect seal, then warmed by residual heat, then expanded, showing as pressure. The cycle repeated slowly, over hours, with the brick setting serving as a heat reservoir that sustained the process far longer than the boiler alone could. The sounds were explained. The knocking came from differential cooling of the iron plates, thermal stress releasing in sudden small movements. The humming was vibration from air movement through the flue passages, resonance in metal structures responding to pressure changes. The sighing was condensate draining through internal passages, air moving to replace it. All mechanical, all predictable, given the conditions, all unsettling to men who expected silence. The engineer made his recommendation: drain the water completely, break the thermal mass that was sustaining the process, allow air to circulate freely through the opened boiler, eliminating the trapped vapor space. The system would reach ambient temperature in hours rather than days. The pressure would disappear because its source would be removed. Simple, direct, obvious once the cause was understood. But he added one final note. This would happen again, every shutdown. Every time the fire was damped and the water left inside. The system was not designed for rapid cooling. It was designed for operation. And in the late 19th century, most boilers ran for months at a time before being drained and inspected. Shutdowns were rare. The slow cooling was normal. What was abnormal was the expectation that a machine this size, this massive, this thermally invested, would cool quickly. It would not. It could not. Physics did not permit it. The factory men absorbed this quietly. The wrongness they had felt, the sounds and warmth and persistent pressure, all reduced to mundane mechanical truth. No mystery, no hidden force, just iron and water and heat, following laws that did not care about human expectations. The boiler did exactly what it was built to do. The men simply had not understood what that was. The water was drained over the next 2 days, slowly, carefully, filling rail cars that carried it away to be discarded. As the level dropped, the pressure fell. The warmth began to fade. The sounds diminished. The boiler house grew quiet in a way it had not been since the mystery began. The iron shell, empty and open, cooled to ambient temperature within hours. The brick setting took longer, radiating its stored heat into the air for days afterward. But without the water mass to sustain vapor pressure, without the thermal feedback loops that had trapped heat inside the system, the wrongness disappeared. The boiler became what it appeared to be, a large iron vessel, cooling in still air, silent except for the occasional tick of contracting metal. Work resumed. The factory returned to its rhythms. The boiler was refilled, refired, brought back to operating pressure. It performed as it always had, generating steam on demand, powering the machinery that turned raw materials into product. The men who tended it had learned something, though they might not have been able to articulate exactly what. Industrial systems are not simple. They obey laws that do not announce themselves. The engineer returned to the city. His report went into files that would be forgotten, consulted decades later, only when someone else encountered the same phenomenon and went looking for precedent. He had solved nothing new. He had only explained what had always been true. Boilers do not cool quickly when their water is left inside them. They release heat slowly, through processes that appear mysterious only because they are not commonly observed. The foreman kept the logbook entries. Read them occasionally, reminding himself that what seems impossible is often only misunderstood. The boiler had not defied physics. It had followed physics exactly. The men had simply expected it to follow a different path, a simpler path, one more aligned with their intuition about how large machines ought to behave. But iron does not care about intuition. Water does not adjust to expectation. Heat moves according to laws written into the structure of matter itself. In later years, other factories would encounter the same mystery. Other crews would stand in boiler houses that refused to cool, feeling warmth that had no visible source, hearing sounds that suggested life in dead machinery. Some would solve it quickly, having heard the story or read the reports. Others would struggle as these men had struggled, certain that something was wrong, unable to see that the wrongness was in their assumptions rather than in the machine. The boiler that refused to cool became a story told in engine rooms and maintenance shops, not as ghost story, not as industrial legend, but as reminder. Reminder that complex systems have behaviors that emerge only under certain conditions. Reminder that what seems obvious during operation may be completely wrong during shutdown. Reminder that humility is warranted when dealing with machines built to contain forces humans can barely comprehend. The river continued past the factory. The seasons turned. The boiler ran and was shut down and ran again, each cycle depositing a little more scale, wearing the valves a little more, aging the iron through stress and heat. Eventually it would be replaced, cut up for scrap, melted down to make something new. But for a brief time, it had taught the men who tended it something about the limits of their understanding, about the gap between how things appear and how things are. Iron does not forgive ignorance. It only waits. Waits for the moment when assumptions fail, when intuition misleads, when the comfortable certainty of experience proves inadequate to explain what stands before you, warm and humming and impossibly persistent in its refusal to behave as expected. And in that moment, if you listen, if you measure, if you set aside what you think you know and look carefully at what is actually there, the iron will teach you. Not gently, not kindly, but truthfully, with the absolute honesty of physical law, applied without mercy or exception. The boiler cooled eventually. They always do. But it cooled on its own terms, according to its own nature, following paths carved into it by the conditions of its construction and operation. And the men who watched it cool learned that machines are not simple tools that start and stop at human command. They are physical systems embedded in larger physical systems, subject to laws that operate whether or not anyone is watching, whether or not anyone understands. The mystery was solved, but the lesson remained.